The first talk in this afternoon is given by Professor Moeckel. He is also the advisor of the Professor Chen Guozhang and So, the title is Relative Equilibrium Configuration of Gravitational Interacting Rigid Bodies. That's Professor Moeckel.
So the movie is two rigid bodies, each one of which is a stick with two masses on it. So it's a rigid body, and then two of them in orbit around each other, moving in a very simple way. And that's an example of a relative equilibrium motion. So from the astronomical point of view, this is a talk about phase locking. So when two astronomical objects rotate around each other, they also spin on their axes. And it's possible that phase locking means that the rotation of the bodies around their axes is the same as the rotation around each other. So that the two bodies will always be pointing exactly the same face towards each other. And the whole system just moves rigidly around as if it were a single rigid body. So everyone knows that the moon, as you look at the moon, it's always showing you the same side. And that's because the moon is phase locked. But the Earth is not phase locked. If you look at the Earth, it's spinning at a different rate. So this is a problem about two bodies, and they're both phase locked. So they're both moving in such a way that they rotate at exactly the same rate as they are in orbit around each other. So not the moon and the Earth, but here's an example in the solar system. Pluto has a moon, Charon, and they're phase locked, at least very approximately phase locked. So they do just rotate around each other and revolve around their axes at the same rate. And there are certain asteroids, two asteroids in the asteroid belt, relatively close together, act as it can be phase locked into such a motion, a very simple motion. And that's called a relative equilibrium motion when they're both phase locked, or all the bodies are phase locked. That's what we mean by a relative equilibrium. So for two bodies, like Pluto and Charon, some of these relative equilibrium states are stable in a certain sense, and they can give an explanation for this phase locking that we see. And so the first part of my talk is about what happens with three bodies. What if you have three asteroids? These are not really asteroids. They're little rocks that I picked up from the front of my house. But imagine they're asteroids out in space. Would it be possible for them to evolve into a system where all three of them are phase locked, and they're just all going around? Their common center of mass is probably somewhere here. So all three of them would just rotate around their center of mass as if it was a rigid motion. So how can we understand this idea of phase locking? So why do things become phase locked? It's because there's some dissipative forces involved. It's not just the usual n-body problem. Somehow energy is being eliminated from the system, usually because of tides. So as the bodies go around each other, they actually are not quite rigid. They expand and contract a little bit. And that heats up, they get hot inside, and energy is taken out of the motion. But according to some models, these dissipative forces, even though there are dissipative forces, the angular momentum of the system and the momentum of the system is left unchanged. So the energy is going down, but the angular momentum is staying the same. So then, if you think of it that way, then it leads to this math problem, a mathematics problem. So take n gravitationally interacting bodies in R3, fix the center of mass, and the total momentum will be 0. And the total angular momentum is some vector in three-dimensional space, let's say just a vertical vector. And look at all of the possible states of the system that have that, those properties. You get a certain submanifold of the phase space. Then you want to find the minimum of the energy, because the energy is going to go down. You'll stay on this manifold because of the angular momentum being constant, but the energy is going to go down. So you'd like to look for minima, or maybe local minima, of the total energy function, but restricted to this manifold. So there are a lot of older works on phase locking, but this question was dealt with by Steve Smale in his famous papers on topology and mechanics. And what he showed was if you look at this problem, you find critical points of the energy function restricted to with fixed angular momentum. That's the same thing as one of these relative equilibrium motions. So a relative equilibrium is a motion like we've seen in the movie there, would correspond exactly to one of these, a critical point, not necessarily a minimum, but a critical point of this energy restricted to m lambda. So there are sort of two main results. The first one is about a negative answer to the question about the 3 rocks. If you have 3 or more bodies, there do not exist any minima or local minima of this energy function on m lambda. So if you're fix the energy or the angular momentum to be lambda and you let the energy go down, there's no bottom to the valley. Every critical point is a saddle point. So there's always another way to make the energy decrease. So this is a general result without assuming anything about the shape of the bodies. They can be very weird looking shapes. It's going to be impossible to have 3 phase-locked bodies if the mechanism is decreasing energy with angular momentum fixed. So what does happen? Suppose you start with those 3 bodies in orbit around each other, and the energy is going down, the energy is going down. What has to happen? Well, they will not become phase-locked. Instead, something else has to happen. So either they must collide. If they collide, they might somehow interact and form fewer bodies. So if you have 3 bodies and 2 of them collide, they might stick together. Now you have 2 bodies. And they might phase lock. That's one option. Another option is one of the bodies will just get thrown out of the system. Somehow they'll interact for a while. One of them will go away. And then the other 2 could become phase locked. As long as there are 3 or more, the energy can keep going downhill. So something else has to happen. So that's one sort of physical implication of this theorem. Another one concerns the reduced mechanical system. So if you have a system, a mechanics problem with symmetry, you can look at the quotient system. You can reduce out the symmetry group. And then a relative equilibrium just becomes an equilibrium because you've quotiented out by the rotations. So that if things are just rotating, if you eliminate the rotations, then now they're just fixed. But the resulting equilibria that you get will never be extrema of the Hamiltonian. And this is basically the only way that you can really prove stability for all time in a Hamiltonian system is if you're at a minimum of the Hamiltonian, or perhaps a maximum. It's not a maximum either. Since there are no minima, you will never have an easy proof of stability for such a relative equilibrium motion. For two bodies, you can. There are minima, and they will be mechanically stable, and also may evolve to this state by energy dissipation. So this was a result known for point masses. If you instead of rigid bodies, if you think about n point masses, and you ask the same question to minimize the energy on a manifold of constant angular momentum, then the answer was already known, and it follows from some computations about Morse indices of these critical points, which go back to Palmore and Smale. But then for the rigid body problem, it was a conjecture made by Dan Scherz. Dan Scherz is an astrodynamics guy at Colorado. And he wrote a really nice paper called Minimal Energy Configurations of Gravitationally Interacting Bodies. And he conjectured this theorem, and I got interested in it by talking to him and reading his papers. There's a lot of other interesting things in those papers. So, for example, you can try to now you can allow bodies to actually touch, and now you can look for, as the bodies roll over each other, what's the minimum energy configuration. So that's another really interesting problem, which is quite difficult, and except in the case where it's just spheres, round spheres, it's more tractable. But I think there's some interesting open problems about this.
Can I ask a question about the Hamiltonian?
Yeah.
It consists of kinetic energy of translation and rotation.
Right.
And gravitational potential.
Yes.
Right. So this statement is claimed for all possible masses and all possible moments of inertia. There's no equilibrium. Is that correct?
There are equilibria, but they're not minimum.
After the quotient.
Yeah. So there will be critical points. There will be equilibria, but they won't be minima of the energy. So the bottom of the energy well is the only thing that's definitely stable.
Right. But this statement is valid for all possible assignment of mass and moments of inertia.
Yes, it's about, you can take, some kind of reasonable shapes, not, fractals, or you have to be able to do certain integrals, some integrable shapes with integrable mass distributions, compact bodies, a few assumptions, but very general. Yeah. And then the second part, which is, if you like topology, is sort of fun, is about just counting, using Morse theory to count in the two-body case. Now you can have, in the two-body case, let's count how many of these relative equilibrium configurations there are. So critical points, not necessarily minima, but how many critical points can there be? How many ways are there for these two bodies to rotate around each other? And the Morse theory comes out under certain assumptions on the masses. This is the Morse theory count for how many critical points, 32 critical points, up to an overall rotation around the angular momentum vector. And then if you, assuming they're all non-degenerate, you have to always assume critical points are non-degenerate in order to do Morse theory. To do, if you don't want to assume that, you can use Lustenich-Schnirelmann theory, and then you get a weaker bound of 12. So it looks like the hypotheses of these two theorems are the same, but actually this one's much larger. This is kind of a limiting theorem in the case that the angular momentum goes to infinity. It turns out that this is a pretty, not that great an estimate. It seems that there's a lot more relative equilibria than 32. And the number, if you take a limit as the bodies get farther and farther apart, which is the same thing as large angular momentum, you actually come up with 576 relative equilibrium configurations. So there's, again, a bunch of open questions about whether you can get a much smaller number than that when the bodies are closer together. I don't know. So the Morse theory estimate, I can do it, but maybe it's not a very good estimate. Okay, so let's talk about mathematically what is the problem. So you have a problem of n rigid bodies in three-dimensional space. So each body, if you want to describe one rigid body, you usually have a coordinate system called body coordinates, where you describe the body, and then a mapping which takes the body and puts it into three-dimensional space, our normal, the space where we live. So this is just a space where it's easy to describe the body, and then there's this mapping into three-dimensional space. So in the body coordinate system, you just have some mass distribution, some measure, some mass measure, this is a compact set that has a certain total mass, which is supposed to be positive. And we're going to assume that in the body coordinate system, the center of mass is 0. And then there will be an inertia matrix, moment of inertia, as you were asking, describing the physical properties of this body in its own coordinate system. And then you put it into three-dimensional space by a translation. You translate the center of mass to some point which will be called Qi. And you also apply, well, maybe the way that I did it here, first you rotate it a little bit, apply a rotation matrix, and then translate it into three-dimensional space. So in order to describe one body, you need to have a three-dimensional vector to describe the center, and a 3 by 3 special orthogonal matrix to describe where how it's oriented, how it's rotated. And then you do that for every body, and so you have a lot of coordinates. So just to describe the position, I need to give tell me where the center of every body is, and give me a rotation matrix for every one of those bodies. And so this is it's a 6n dimensional manifold. SO3 is 3-dimensional also. So it's a 6-dimensional manifold of configurations just to describe the positions of these bodies. And so in the configuration space, we also want the center of mass to be 0 of the whole system, and the bodies should be disjoint. We don't want them to interpenetrate one another. And that's just an open subset of this plane. Well, the center of mass describes a subspace, and then the bodies have to be disjoint. And then the actual dynamics takes place in a phase space where you have velocities also. So we also have 6n velocities. Tell me how fast the center of mass is moving, and also the angular velocity of the rotation of the body. And then it would be a Lagrangian system where, depending on all these 12n variables, and again, as you said, there's a kinetic term and a potential term. The kinetic energy term is relatively standard, just involving how fast the bodies are moving and how fast they're spinning around their axes using those inertia tensors. But the potential is very hard to understand for strange shapes like this. It's every point in this body is gravitationally interacting with every point in that body. So you have to integrate the Newtonian potential over both bodies. So you end up with a 6-dimensional integral, and that's just for 2 bodies. For each pair of bodies, you have a complicated integral to do to figure out the potential energy. and then you add that up over all possible pairs of bodies, and you get the total potential energy. So the potential is really quite complicated, and that makes this problem hard to understand. If you want to do the dynamics, it's really quite complicated. So what does a relative equilibrium look like? Well, it's a rigid rotation. Everything is just rotating rigidly around some axis with some angular speed. So we might as well, you might as well assume that it's rotating around the vertical axis, 0, 0, 1. So imagine everything is just rotating around this axis at constant speed, angular speed, omega. Then this would be the angular momentum. The resulting angular momentum would be, again, even for one, if you're familiar with one rigid body, just because you know the angular velocity doesn't mean you know the angular momentum. The angular momentum could be pointing in some other direction. And you get from the angular velocity to the angular momentum by multiplying by an inertia tensor. So there's an inertia matrix, a 3x3 matrix, which you apply to this 0, 0, 1 times omega vector, and that gives you the angular momentum in general. And it's a complicated, depends on the centers of mass and the rotation matrices and these little inertia tensors. But it's basically a quadratic thing, some kind of quadratic expression. But for a relative equilibrium, it turns out that that both of these vectors are pointing in the same direction. So you have the angular velocity could be some multiple of this, and the angular momentum is also a multiple of that. They're all pointing in the same direction. And which is to say that that lambda is an eigenvector of this matrix. And or E is an eigenvector of this matrix, or eigenvector, and then the eigenvalue is this thing I'm calling G. So the lambda is just some multiple of the angular velocity direction. Again, the formula is not so important. It's not. It looks long, but it's just quadratic, some quadratic expression. And then it turns out that you can characterize the relative equilibrium as critical points of what's called the amended potential function. So this goes back to Smale again. Well, it's sort of simple looking, but it actually involves the inverse of this 3x3 matrix and these vectors, the lambda vector, plus the potential here, or minus the potential. And in Scher's work, he replaces the amended potential. I'll tell you in a minute where this comes from, the amended potential. But then Scher's works with a simpler function. If you take this lambda here and you replace it by the value that it has at the relative equilibrium, which is an eigenvector, it's an eigenvector of the inverse as well, and then the whole thing simplifies down to this. This first term is much simpler. It just involves the length of the angular momentum, and there's a scalar, instead of a matrix, instead of this 3x3 matrix, we just have this scalar function in the denominator. So that's what he's calling the critical energy function. And one of the theorems along the way is that these two guys actually have the same critical points. So if you're looking for relative equilibria, you could look for critical points of this, but you could also look for critical points of this. And this one is much simpler. So this is the one that you would like to use to do the theory.
Is there a simple argument why alpha is an eigenvector that's relative everywhere?
I don't know why. I don't think it's terribly simple, no. Yeah, I mean, I guess we know that the angular momentum vector should be constant. I mean, if you think about a single rigid body, that's the way it is. So you have the principal axes. For the, one rigid body has principal axes. And if you try to rotate it around some arbitrary, so it would be this axis, or this axis. So there's a relative equilibrium like that, and one like that. But if you try and rotate it around this direction, it kind of tumbles. So if the angular momentum vector is off this way, the angular velocity is going to change. So for one rigid body, it's sort of a familiar thing that that's the only way to do it around the principal axes. And the principal axes are exactly the eigenvectors of the moment of inertia tensor. So that's something. I don't think it's terribly simple in general. Yeah.
But if there's no friction, it will remain that way.
Right. Yeah. So the relative equilibrium they really are equilibria in a sense. They will stay that way. They're not dissipating energy anymore because they're critical points of this function. Right. So the idea behind the amended potential is pretty simple. In principle, it's basically you start out with a problem in the phase space. Namely, you have this energy function which depends on all the positions and all the velocities. And you're looking for critical points of that. So that's 12n variables in this case. And we want to reduce that to a problem about the critical points of a function which just depends on the configuration variables. So you need to eliminate the velocity variables somehow. And the method is just to imagine hold all these variables constant and then minimize this function over the other variables. So find the minimum with respect to the velocity variables. And the reason there's a minimum is because if you fix the angular momentum, that defines a subspace of velocity space. And then the energy is basically just the kinetic energy that you're minimizing, and that's a quadratic form. So if you have a subspace, and an affine subspace, like let's just say an R2, well, you have some subspace, and you want to minimize a quadratic form like the square of the distance to the origin, there's a unique minimum point. So this would be like all the velocities that you're allowed to look at, and this is the place where the size of the vector squared is 0. So this is like minimizing the norm of v squared on the subspace. And because it's a quadratic form, there's always a unique minimum. It's a non-degenerate quadratic form. So then you get this unique velocity vector, and you plug it in, take that velocity vector and plug it in here, and now you have a function which depends only on the positions. And that's the definition, really, of the amended potential. So just minimize over the velocities first. And now, since we wanted critical points of this, now you just have to find critical points of this. You already have a critical velocity. Now you just have to find a critical point of this this function. So that's how you get it down to configuration space. Okay, so what we really are interested in is, for the first part of this talk, is about minima and showing that they don't exist. So if you want to minimize this function, you've already minimized over the velocities. So now what you have to do is minimize this function. So if you show that that function doesn't have any local minima, then that would prove it. And then so there's a lemma that says, oh, I can replace that by this simpler function. So remember, there's these two functions, one of which is easier to work with. This is the amended potential, but this is the one that Shears came up with. So I want to minimize. I'm going to really work with this one if I can. So there's this lemma that says, okay, if you're looking for minima of this, basically you can go ahead and look for minima of this instead, except if some technical condition is not satisfied. So that's unfortunate that there's this technical condition, which I don't really know if it's necessary, but that's the best I could do. And so now, how do I show? The main theorem says that if n is bigger than or equal to 3, there are no local minima of this h h on this m lambda. So show that there's no local minima of this first. And how do you show that a function is not a local minimum? Well, you should look at the second derivative at the critical point, the Hessian matrix. So we have this a very complicated matrix, a 6n by 6n matrix. So we have this Hessian matrix. Well, maybe it's 12n by 12n actually. No, 6n by 6n, because we're down on configuration space. Sorry. And I want to show that that matrix is not positive definite. So if it was really a local minimum, this matrix should be, or positive semi-definite at least, to be a local minimum. If it has a negative eigenvalue, it means there's some direction where the energy goes down. So I want to show it has a negative eigenvalue. And instead of doing that, I work with this block. If the thing is positive semi-definite, this 3n by 3n block is also positive semi-definite. This is the matrix of second partial derivatives with respect to the q variables, qi variables. So you can look at a partial Hessian where you don't rotate, so you're just kind of moving the bodies, you're translating the bodies. You're not rotating them. So if you can make the energy go down just by translating the bodies, then you can make the energy go down, then the energy goes down. So you know it's not at a local minimum. So how can you see that you can make the energy go down just by translating the bodies? You can try to find a negative eigenvalue for that matrix, that smaller matrix, 3n by 3n matrix. And it's very complicated, though, because of the potential energy is so complicated. So instead of that, it suffices just to show that the trace of this matrix, take the trace. If the trace of the matrix is negative, then it's not positive definite. So it suffices to show that the trace is negative. The trace of that block is negative. And it turns out there's a simple estimate for this trace. So the trace of that little block actually is strictly less than this number. And that's perfect for what I want to do, because when n is bigger than or equal to 3, this number is 0 or negative. And trace is strictly less. So for n greater than or equal to 3, the trace comes out strictly negative, meaning that there's a direction. You can translate these bodies in a certain way, and the energy, the critical energy function will go down. So this, you might think this is a really difficult thing to do, but it's actually not technically too bad, because there's a way to get rid of the contribution of this very complicated potential function to the trace, not to the Hessian actually, but to the trace of the Hessian, turns out to be 0. So really, you're really just dealing only with the kinetic term when you do this computation, which is where this estimate comes from. And it's actually intuitively not too hard to understand why this should be the case. If you just remember that the function 1 over r in three-dimensional space is a harmonic function. So if you ask the same problem about a harmonic function, so basically you have this 3n by 3n matrix, and it really has some 3 by 3 blocks. And a harmonic function means that if you have just an ordinary harmonic function in three-dimensional space, by definition is a function like that. And that exactly says that if you look at the 3 by 3 Hessian matrix, the trace of that Hessian matrix is 0. So essentially, that's the kernel of the argument, is that first you just get down to this question about the trace, and then it turns out that when you look at all these blocks, the fact that the Newtonian potential function 1 over this function is basically the Newtonian potential function, that's a harmonic function, forces the traces of all these blocks to be 0. Okay, so that's the way the proof goes. A bunch of little lemmas and stuff on the way.
But there's a kinetic term which is compact.
Yeah, that's where this comes from. That's where this comes from. The kinetic term.
That's what.
It's the term. It's the kinetic term in this. It's not. Yeah, it's sort of this term here. It's positive if you change this, but I'm messing with this. So you have to differentiate that. Yeah, so the contribution of this term is 0. You need to calculate the Hessian of this guy and estimate it. Yeah, so it's clear that this is a positive definite quadratic form with respect to lambda. You know, if you rotate faster or something like that. But what happens when I move the bodies? Then the inertia tensor changes. It's how the inertia tensor varies when you vary the bodies. Yeah. But really, it's how it's actually, since this is constant, it's really how this varies. You know, somehow it all goes down to how this thing varies, or here's the g function. Yeah, so these are being held constant. You're differentiating with respect to these. And it's in the denominator. Yeah, I can't remember exactly how that comes out. But it's just a computation. Okay, so the second part of the talk, I'll just kind of go a little quicker here because maybe it's less interesting than the first part, or it's fun, but it's fun topology. So what if you just have two bodies? Let's go ahead and count the critical points of this this critical energy function. This is the simplified version of the amended potential. And now we only have 9 variables, because you can, if you fix the center of mass, you can just, you don't have to have Q1 and Q2. You can just tell me what this vector is. You can, by using the fact that the center of mass is 0, you can replace Q1 and Q2 by a single vector, just the vector that goes from one center of mass to the other. So there's just a single vector telling where these bodies are with respect to each other, the translation part, and then 2 rotation matrices. Still have 2 rotation matrices. So this is 3 dimensions, 3 dimensions, 3 dimensions. So it's critical points on some 9-dimensional manifold. And all the formulas. And actually, if this is a critical point, so is this. You know, there's actually circles of critical points. So to eliminate that, you can kind of rotate these guys so that this vector is in this vertical plane, the plane of the blackboard, XZ plane. So that gets you down to 8 variables. And you want to count critical points. Maybe I won't do this. So again, I have these two rigid bodies, and there's a vector between them. Now, they're pulling at each other, right? And I want to rotate around this axis. So if one of them is really strictly above the other, that's not going to work, because this one's going to get pulled up and this one's going to get pulled down. It's impossible that they're just going to rotate around like that. They're not going to rotate around like that. It'll be pulled down. So you can, a priori, you can restrict the Z, you can restrict this direction, the separation here. And then if I move them too close together, they're going to intersect each other. So you can, it's not easy to see this. There's a little rectangle here in the XZ plane that I'm restricting to now. So So again, if the Z coordinate is too big, it's not a relative equilibrium. If they're too close together, it's also not a relative equilibrium, because they're hitting each other. And there's a way to say that for a given lambda, there's a way to put an upper bound on it as well. And then there's the 2 rotation matrices. So you have SO3 cross SO3 here. So you have a little rectangle. That's my 8-dimensional manifold. It's a rectangle crossed with 2 copies of SO3. And I'm trying to find critical points of this H lambda. Well, under certain conditions, the gradient of H lambda is pointing out on the boundaries of the rectangle. So that's a little lemma. And then you can do Morse theory. You can count critical points here by the topology of this manifold. So, for example, if these SO3s were not there, and you just saw that picture, you'd say there has to be at least one minimum inside there. There's got to be some minimum of that function. If the gradient's pointing out everywhere, there's got to be at least one critical point in there somewhere. That's a pretty bad estimate, but I mean, if you have these now, the topology of these things produces complexity, and you have to have a lot more critical points. And that's what Morse theory does for you. You need to calculate the homology groups of this space. And so that's what I'm calling chi, this space. And then it turns out there's a Z2 symmetry as well, which again, I don't want to belabor all this, but this is really the space. And what was I calling that? Like chi mod Z2, I guess. If this is a relative equilibrium that can rotate around like that, then if I flip it, it's also a relative equilibrium that can rotate around like that. So it's if you have one critical point, you have another critical point. There's a Z2 action that you can eliminate. And when you're counting critical points, it's always good to use as much symmetry as you can. Going to skip that. So the space I'm interested in is this space. And I need to know the topology of that space. So the rectangle has a trivial topology. It's a contractible space. It has the topology of a point. So it's really the topology of SO3 cross SO3 mod V2 that matters. By a little trick, the action, this is the Z2 action, it's just multiplying by that matrix. You can move it onto the second factor by a little trick, standard sort of trick. And so the topology of this space is really the same as the topology of SO3 crossed with SO3 mod Z2. So if you've studied Lie groups or something, you probably know about SO3. So SO3 is the real projected space of dimension 3. And that's a well-studied topological space. But but what about SO3 mod Z2? That's a less well-studied topological space. But this one, it's a familiar fact that this Lie group is double covered by the 3-sphere. So the rotation group, if you think about quaternions, unit quaternions, there's a double covering of the rotation group by the 3-sphere. So this space is really SO3 mod Z2. And I want SO3 mod Z2, so that's S3 mod Z2 mod Z2. And it turns out that one is the same as S3 mod Z4. Okay, so there's a finite group action on the 3-sphere which yields this space. And in fact, this is kind of the coolest part, is that turns out to be a lens space, one of these lens spaces. So whenever you take an algebraic topology course, they bring out these lens spaces as an example of calculating homology groups. A more complicated example. It's not a sphere, it's not a projective space, it's something else. And this is called the lens space L14. And these were invented by the hero of dynamical systems theory, Henri Poincaré. So it's kind of Poincaré's other activity besides celestial mechanics and dynamical systems was he invented algebraic topology and manifold theory, and he invented these as examples in homology theory. So I was really thrilled to see a lens space just come up. You know, a lens space just happens to be the right space in this particular problem.
But this V2 is from time reversal, right?
It's two things. So if you have something like this and you rotate the whole thing upside down, it's now going the wrong way. But if you now reverse time also, yeah. So it's a double. The Z2 action is so right there. If I have this, if this is a relative equilibrium, and I rotate the whole picture upside down, it's now going the wrong way. The angular momentum would be down instead of up. This one has the angular momentum vector up, but when I flip it, it has the angular momentum going down. But if I also reverse time, now the angular momentum vector is going up again. Yeah, so that's the Z2. So then you need to get out your algebraic topology book or consult with your colleague or something and figure out, I got out my book actually, figured out what are the cohomology groups. And to do Morse theory, you need cohomology with coefficients in a field. So C2, what's a great field? So these are the homology, the coefficients here are the homology groups of RP3. The zero-dimensional homology, all of them have rank 1 as vector spaces over Z2. So 1, 1, 1, 1 are the coefficients of what's called the Poincare polynomial of projective space using Z2 coefficients. And then it turns out that if you use Z4 coefficients, 1, 1, 1, 1, 1 is the same thing for the lens space. But then you have to convert that to Z2 coefficients, and it comes out to be 1, 1, 1, 1 again. So, but it's, you know, a page of exact sequences or something like that to prove that. And then you have a product space of two things. I have a product space of this and this. And then there's a theorem that to calculate the Poincare polynomial of that, you just multiply the two Poincare polynomials. So I just take the square of this, and I get this. And this says that in this quotient space, there has to be the zeroth homology has rank 1, the first homology has rank 2, rank 3, rank 4, rank 3, rank 2. The sixth-dimensional cohomology has rank 1. And that means by Morse theory there has to be at least one minimum, 2 saddle points with a Morse index of 1, 3 saddle points with a Morse index of 2, etc. So this gives you a lower bound for the number of critical points. And the total lower bound is the sum of all those things, which is 16. And then if you undo the Z2 action, you get 32 critical points back in the original space. So that's why it's good to do this Z2. Do the count with the Z2 out of there, and then you get twice that many when you go back. And if you know anything about Lucian experimental category, if you don't have non-degeneracy assumption, you need to use this category, which has to do with cup products. So now you need to know the cup product structure in that space. So you know, motivation for algebraic topology, I guess, because you really need to know these numbers. And that comes out to give you a bound of 6, which when you double it gives 12.
So this should have 6 points or
no? No. Yeah. So now the final thing is about this 576. So when the bodies are far apart and you get a limiting problem, and the only thing that matters is the principal axes of the bodies. So if the principal axes are aligned, it's a relative equilibrium. Those are all the relative equilibrium. It's all the ways to align the principal axes of two bodies. I indicated that with some dice. So next time you teach probability, you can ask your students how many ways are there to put two dice down on a table facing each other. So you got to choose which faces, and then once you choose the faces, you can still rotate 4 different ways around here and here. You get 6 times 6 times 4 times 4, which is 576 different ways to put the dice down on the table. And those would be, all of these are relative equilibria in the limit. So that's a relative equilibrium, that's a relative equilibrium, that's a relative equilibrium, and so on. And, you know, turning this around, it's a different one in general. So 576 is the count that you get. Just listed a few what I think are interesting open problems. Can you get less than 576? I hope so. But it would have to be shapes that, if you have things that are really symmetrical, like these well, these are not quite symmetrical, but if you have discrete symmetries, you're going to get a lot just because of the symmetries. As you lower the angular momentum, you get bifurcations in the number of relative equilibria. This is still for n equal 2. Can you ever get more than just the 2 minima? Or, well, the expected number of minima. What about irregular bodies in contact? What's the minimum when these two erasers are in contact? complicated. For n equals 3, this is probably a relatively easy problem. Can you find a relative equilibrium of 3 bodies? We know that there are no minima, but maybe it's still dynamically stable. It could be linearly stable. There are examples with point masses which are linearly stable, but they're not minima. So you have a relative equilibrium that's linearly stable without being a minimum of the energy landscape. And then if you have 3 bodies, the implication was that they can't phase lock. So what do? So it'd be nice to have a simple model of the tidal evolution of 3 bodies, which allows you to decide whether 2 of them come together and form a single body, or does one of them get ejected from the system. So that will depend on the initial conditions. And it's more of a dynamics problem rather than just looking for the equilibrium problem. Okay, so I think that's it. I'll just put this up. Okay, thanks.
So, any question?
If I remember correctly, so the 4 body relatively clear on the plan. The
Yeah.
lower bound is also 32. Is that a coincidence?
Probably, you mean for 4-point masses in
Yes.
the plane. That's got to be a coincidence, yeah. Even though that looks like 4 bodies because I made little stick figures.
Yeah, is that right? So the lower bound is also 32.
But the Morse theory bound is, you're saying the Morse theory bound is 32? Yeah, maybe.
Yeah.
That sounds right. Yeah. It's probably a coincidence, yeah.
The actual force is, does it preserve the angular momentum, or it moves the angular momentum?
You mean if I put them into 4-dimensional states?
Even it's 3-dimensional.
Well, probably, I don't know. There's an SO4 symmetry for the 2-point mass problem. I actually don't know how that generalizes to 2 rigid bodies.
Okay, so
Because for the rigid bodies, you know, it's sort of obvious that the potential is unchanged, but I think you'd have probably not a symmetry. Yeah. Yeah, it's an interesting question. Yeah. I think even for the point mass problem, it probably does not.
preserve the
Yeah.
angular momentum. Okay.
Yeah. Yeah.
So if there is no more, let's thank speaker again.